All right, so we're discussing Dalton's law of partial pressures. And to put a little equation to that, that's real simple. The total pressure is equal to the pressure of gas 1, the pressure of gas 2, the pressure of gas 3, and the pressures of however many other gases you have. What's interesting about this is all the gases, as long as they're not combining, reacting with each other, think noble gases as an example, they all behave independent of each other. So the gases kind of, again, behave like there's nobody else in the container than themselves. So you could have 1,000 atms of pressure of argon gas in there, and then you've got some CO2 gas in there, say 1 atm. That 1 atm behaves as if it's the only 1 atm of gas in there. It doesn't behave any differently, even though it's got 1,000 atms of pressure of argon gas in there. It's all done. All right, let me put a little equation kind of stuff here together, and then we'll talk a little more once I get this all down. We're talking about mole fractions. And it looks a little messier than it's going to end up being. So I've got a pressure of gas 1, and just utilizing the ideal gas law. So that's 1 gas, and then I have a total pressure of all of these gases in there based on the number of moles. I'll put a 1 here and a T there as well. So total number of moles and total amount of pressure. Now, because this is all in the same container, I can summarize some of this and say it's simply 1 mole out of the total number of moles. And I'm going to change it around to X1, which is the same thing we're talking about here as being a mole fraction. So again, it looks messier than it needs to be. Let's continue this for a few minutes. Therefore, the pressure of a gas out of all of the total pressures in a container has a ratio represented of the moles out of the total, or again, equal to 1 over that. So again, really what we're looking at here is just the ratio. So if I know the percentage that this mole is out of the whole, I can apply that to the total pressure in the container and figure out what its individual pressure is of that gas. So I'll write this again. Pressure 1 based on, I'll say, X times the total pressure in the container is going to give me the pressure of that 1 gas. So if I know this is 75%, the pressure will be 75% of that 1 of the total pressure within the container. That's it. Okay, let's do another problem in the homework. Bring this over, and I think we're on 63. Here we go. Consider the apparatus in the drawing, following drawing. So let me draw this out here first. I've got a container, and there's a split in here, if I'm not mistaken. On this side, I have nitrogen gas, and it is 2 liters, and it is 1 atm. On this side, I have oxygen gas, and it is 3 liters with 2 atms, excuse me. Okay. When the valve between the 2 containers is opened and the gases are allowed to mix, how does the volume occupied by the nitrogen gas change? So how does the volume change? Well, it was in 1 liter and now it's in 3 liters. I can do that. It was in 2 liters, now it is plus with 3 liters, so it is 5 liters. So we'll say 5 liters right there. Just put that in there. What is the partial pressure of the nitrogen gas afterwards? So interesting how we're going to look at this one here. This is a little bit of a different question here as far as how we're going to approach it. We know the initial conditions. What are the after conditions. So this is maybe a little bit misleading based on how I kind of set this up. So originally, the nitrogen gas is at 1 atm, and it is at 2 liters. That is how we're setting it up. The question is what is the partial pressure after mixing? So be careful how you answer that. Well, after they mix, what's my volume? 5 liters. These guys are not going to react. We're stating that right now. So what is going to be my new pressure in ATMs? I don't know. We have to figure that out. If we do the math here and solve for x will equal 0.4 ATMs. How does the volume of the oxygen change after they mix? It is also in 5 liters. What is the partial pressure of the oxygen in the mixture? Same deal. I start off at 2 ATMs and 3 liters, and after the valve is opened, the oxygen can go all the way through, and it's at 5 liters. So what is my new ATMs? It's going to be X 1.2 ATMs, total pressure. Now the final question, based on the law of partial pressures, is, flipping it over here, what is the total pressure after the gases mix? Well, just using this one as a reference, again, we already did this work. Here's the pressure of the nitrogen. Here is the pressure of the oxygen. They act independent of each other, so we simply just add them up. So pressure total is going to be equal to the pressure of the nitrogen gas plus the pressure of the oxygen gas. So that is 1.2 plus 0.4 is equal to 1.6 ATMs. And that's it, that's the end. All right, let's go on back to the notes. Okay, kinetic molecular theory. And some deviations. How does it not always follow suit with that? Let's get a couple principles out of the way. First, molecules are in constant random motion. Always bouncing around, hitting each other, hitting the walls, changing speeds. 2, we just make these assumptions. The combined volume of all the gas particles is negligible. 3, we assume that the attractive or repulsive forces are also negligible. So we can ignore those. 4 out of 5, the average kinetic energy is constant at constant temp. So also understand that any particular particle has whatever energy it has. They're different, but the average for all of them is constant at some specific temperature. Last one, kinetic energy is proportional to temperature changes. So they kind of go hand in hand. Okay, so that's something we kind of go on, but we know that this isn't perfect. There's some deviations from this. So we try to pretend this is how ideal gases work, and we kind of go along with that, but it doesn't actually work. So I'm going to kind of scribble some notes over here on the side and show you what's a little off. There are attractive forces. And molecules do take up space. So that's not true. So someone who fixes that is called van der Waals. And he makes some adjustments to the ideal gas law equation. He adjusts Pivner equation. And what he does is he has an additive effect onto the pressure and a subtractive effect onto the volume to make individual specific gases more ideal. Understanding that pressures will normally be lower because of the attractive forces. Particles are actually attracted to each other. So therefore, the pressure you observe is going to be too low. So for a particular gas A, we add in a correction value that raises the pressure value back up to where it should be. Now, because of the volume that particles do take up, the volume value is going to be observed as too high. Therefore, for a particular gas, there is a subtractive value that will knock the value back down to what we want it to be as an ideal gas. So A and B, A is an additive value for the pressure, and B is going to be a subtractive value because of the volumes the particles actually have. And I'll write some of that more down for the next lecture.